Hello, this is the pre-recorded version of our EC 2024 conference presentation of our paper Monotone Randomized Apportionment. My name is Jamie Tucker-Foltz, and this is joint work with José Correa, Paul Gölz, Ulrike Schmidt-Kraepelin, and Victor Verdugo. Our paper initiates an axiomatic study of the space of randomized apportionment rules with respect to a fixed house size. If you've never seen the apportionment problem before, it's very simple. You're just given a list of positive real numbers, and you need to round it to integers while preserving the sum. A notable application of this task is determining how many seats each state gets in the United States House of Representatives based on its population, or in some parliamentary democracies where voters vote for parties rather than candidates, determining how many seats each party should get based on the number of votes it receives. In both cases, we need to solve this rounding problem. To give a concrete example, suppose that we have a country with a legislature that just consists of exactly 11 seats, and it has 6 political parties. And suppose we have an election where Party 1 gets 110 votes, Party 2 gets 270 votes, etc. I've listed the vote tallies in this table and in the bar chart. And we have to determine, based on those vote counts, how many seats each party should get. Remember, there's 11 seats total. So the first thing we can do is define the party share of Party I, this number QI, also sometimes called the standard quota of Party I, to be the number of votes it received divided by the total population. So that's a number between 0 and 1. And then we scale that up by multiplying by the target house size, which is 11 in this case. That gives us 6 numbers that sum to the target house size that are proportional to the number of votes they received. So this is kind of like how many seats each party deserves, right? So Party 2 deserves 2.7 seats. And if these numbers all happen to be integers, then we're done. You should just give each party a number of seats equal to its party share, and then that's exactly proportional. That's obviously the right thing to do. But in general, of course, they're not going to be integers, as they're not in this example. So we have to figure out who gets rounded up, who gets rounded down. That's the apportionment problem. So we're going to take as a non-negotiable axiom the quota axiom, which says that each party I should get either their party share rounded down, which is called the lower quota, or rounded up, which is called the upper quota. So we can start by just assigning all the parties a number of seats equal to the lower quotas. And at that point, we've given out 8 out of the 11 seats. And so there's 3 seats remaining. And for that, we need to look at the residues, which are the parts after the decimal. The residue of party I is notated PI and is defined to be QI minus floor of QI. So the party share minus its lower quota. So based on how we define these party shares to add up to the total house size, is not too hard to see that the sum of all the residues is going to be an integer, namely the number of remaining seats we have to allocate. And that number we're going to call k. So in this case, k equals 3. All 6 of these numbers are between 0 and 1, and they sum up to k equals 3. So which 3 parties should be given extra seats? Who do we choose to round up? Well, one intuitive thing you might suggest is to just take the 3 largest ones. Those seem like the most deserving. So we see a 0.7, a 0.7, and a 0.8. We'll give those 3 the extra seats, parties 2, 5, and 6. And that policy is known as Hamilton's method. It was proposed by Alexander Hamilton to handle the United States House apportionment problem. Not actually what the United States uses in current day. But, that's a fair policy, but it definitely has some disadvantages. There are still winners and losers here, and you can make other arguments for who should have gotten the seats instead. Certainly giving it to the people with the parties with the highest residue seems like a fair idea, but it's still got some unfairness to it. And in particular, another specific problem that Hamilton's method suffers from is the following paradox, where we can imagine rerunning the election with a different voter turnout, and we see that a strange thing happened. So in this election, we see that Party 4 received fewer votes but got an extra seat, whereas Party 6 received more votes but lost a seat. This is known as the population paradox. We say that Hamilton's method fails the axiom of population monotonicity. And in fact, there's a very famous impossibility result by Belinsky and Young that there is no deterministic apportionment method that satisfies the quota and population monotonicity axioms together. Okay, so what can we do? There's drawbacks to deterministic apportionment rules. So we can try to solve this with randomness. The very best thing we could hope to do is the following. It would be awesome if we could randomly select the k parties to round up while we satisfy the following axiom. Each party I want to be rounded up with probability exactly equal to its residue pi. And what that implies is that in expectation, each party gets a number of seats exactly equal to its party share. Whereas ex post, they're getting at least that up to 1. They're getting either, if we satisfy the quota axiom, they're at most getting 1 away from their party share. So it's a sort of best of both worlds fairness guarantee if we can satisfy this property. Ex ante, you get exactly what you deserve, and ex post, you get up what you deserve up to 1 seat. And so one thing you could do to satisfy this is just independently choose whether to round each state up, with each party up with probability pi. But the drawback there is now you don't get any fixed house size. The house size is going to be variable. So what you can do instead is try to correlate the roundings together so that if you round one party up, you round another one down, and then you get the right house size. But it's not exactly clear that you can always do this and for a general residue profile for any k and any n. However, it is true that this is possible, and in the context of apportionment, this was first shown by Geoffrey Grimmett in 2004, and he devised the following method. We take the residues and line them up on a number line between 0 and k. Remember, the residues all sum to k. And then we're going to shift the residues to the right by a uniformly random number drawn between 0 and 1. Okay, so let's suppose this is the shift we get, this little tiny small black rectangle in the corner. And then we look at which of these blocks intersects an integer tick mark on this number line from 0 to k. And each of those parties, we're going to give an extra seat. So in this particular example with the really small shift, parties 4, 5, and 6 each get an extra seat because those are the ones that intersected by the tick marks. And if we got a bit of a larger shift, then it would be parties 3, 5, and 6, etc. So you can see that both of these possible scenarios occurred with probability 0.1. And I've gone and calculated all the other possible shifts that could happen and their respective probabilities. So these are all possible outcomes from running Grimmett's method on this example. Okay, so we always get exactly 3 parties rounded up. Each of these columns has 3 parties in it. And if you look at any particular party, the probability that they are rounded up is exactly equal to its residue. It's not too hard to prove that this satisfies this property. Okay, so it seems like we're done. We've satisfied this ex post quota and ex ante proportionality. It seems like everything you could possibly want from a randomized apportionment method, right? It's going to be fair in a very strong sense. Any way you want to define monotonicity will satisfy that because your expected number of seats is just your party share. So it seems like we're done. Book is closed. That is what randomized apportionment can do. It can get past all these problems of deterministic apportionment. And so this was proposed 20 years ago, and our paper seeks to reopen the book on the space of randomized apportionment methods and say, actually, there are other ways that you can satisfy these axioms, and some of them are actually better than others. And in particular, the issue we draw with Grimmett's mechanism is it leads to bizarre correlations between the selection probabilities of various states. So for example, in this instance, you can see that parties 1 and 2 are never selected together. They never appear in the same column, whereas parties 5 and 6 are very often selected together. Okay, and so this feels a bit funny to us. And of course, Grimmett realized this as well, and his proposed solution was just to randomize the order of the parties. And that will go some way to getting rid of these correlations, but it won't take care of all the problems. And so what we want to do is impose axioms on these apportionment rules to sort of refine the space of possible rules we could use and see which ones are better than others. And what we will find is that Grimmett is not the best one to use. Okay, so why do these correlations matter? Well, here's one specific scenario where they might matter. Suppose in this example that parties 1, 3, and 5 are left-leaning parties. I'll color them in blue. And parties 2, 4, and 6 are right-leaning parties. And so they naturally might want to form coalitions with each other to get a majority in parliament. But just based on the lower quotas that we've handed out so far, we see that we've given out 5 red seats and 3 blue seats. So because the legislature has size 11, you need 6 for majority. So it's up for grabs which coalition is going to control majority. But in fact, if we use Grimmett's mechanism, it's not up for grabs because you can see in this example that there is no column in which all 3 blue parties are selected. So no matter what, the red parties are going to have a coalition controlling government. However, now let's suppose that the populations change, the voter turnout changes, the party chairs change. In particular, we're going to suppose we rerun an election in a way such that the party shares of the red parties all increase and the party shares of some of the blue parties decrease. Okay, now if we run Grimmett's method, we see that the residues line up in this nice repeating pattern. And now you can see that with a shift between 0.9 and 1 will end up actually selecting all three blue parties. So this is a sort of similar sort of paradox as we had before, except it's now about joint probabilities of multiple parties getting together to control parliament. We had a shift in party share that should have only benefited the red parties. It was red parties increasing share, blue parties decreasing their shares, yet the probability of a blue government increased from 0 to 0.1. So this is a sort of bizarre paradox we seek to eliminate. In a bit more formality, we say that a rounding rule is a map R from the space of residue profiles, which are just n numbers summing to some integer k less than n, to distributions over sets of size k of the n parties. And we're going to always require that a rounding rule satisfies the proportionality axiom. The probability that a given party I is included in the random set S is exactly equal to pi. Our fundamental definition of monotonicity is called selection monotonicity. It says that if we have some coalition T, and then we shift residues from some profile P to P prime, where all parties in T increase their residues and all parties outside of T decrease their residues, then the probability of selecting T should increase. So this is exactly what was violated on the previous slide. The previous example shows that Grimit's method does not satisfy this axiom of selection monotonicity. However, it turns out there's actually substantial literature on so-called dependent rounding rules in statistics and computer science. And on this slide is a reference if you want to read more about some of these applications for specifically for approximation algorithms. And we have looked at several of these rules to try to see if maybe some of them do satisfy this notion of selection monotonicity. And we're very dismayed to find that a lot of the rules actually don't, and in quite in surprising ways with the very subtle counterexamples. And I don't have time to talk about it in this talk, but if you read our paper, we go through several rules and show counterexamples for them. However, we did find one rule that does satisfy it, and that is known as Samford rounding. So Samford rounding is the following rule, which is going to define a distribution over sets of size k through the following sampling algorithm. We're going to imagine sampling k parties sequentially with replacement. So I draw a party from my magic bag, and I draw the first party with probabilities proportional to the pi residues. Write that down, put it back in the bag. Now I sample the remaining k-1 parties from a different distribution. Instead of sampling in proportion to pi, I sample in proportion to pi over 1 minus pi. Okay, so just the first one was different. All the rest I use this distribution. And so I'm doing this with replacement, putting them back in the bag each time. And so it's possible that I'll sample the same party twice. If that ever happens, I reject, restart the whole process, and I keep repeating until I get k distinct parties, and then call that my sample. Okay, so this is a bit of a strange rule. Why am I using this pi over 1 minus pi and then doing this rejection process? It's very unclear that this actually satisfies proportionality. But in fact, yes, it does. It just magically happens that the probability of including any given party I is exactly pi under this rejective process. It's a very magical fact. And additionally, we prove in our paper that Samford rounding satisfies this axiom of selection monotonicity. So this is the main result of our paper. And the main sort of policy takeaway is that if you want to use randomized apportionment for your up-and-coming democracy, don't just use Grimit's method because it was the first one proposed. It is this method, Samford sampling, satisfies all the axioms that Grimit's method satisfies and more. It doesn't have these bizarre non-monotone correlations. So I'm not going to go into the proof of this fact. It's very long and technical. I do want to say a bit more about some stronger axioms of monotonicity than what we might want. Because selection monotonicity is really just concerned with this one part of the apportionment pipeline, where we take in as input our residues and use some rounding rule to determine who gets rounded up. And it's just about monotonicity of that process in terms of the entire set being rounded up. However, this is really just one step in this pipeline where we really care about how the total number of seats a party receives, specifically the probability of getting, say, a majority in parliament, depends on the initial vote shares, not just the set who gets rounded up depends on the residues. And so considering this end-to-end process and requiring that to be monotone, we get a stronger notion of monotonicity, which we call threshold monotonicity. For any threshold m, if the shares of parties in T weakly increase and the shares of parties outside of T weakly decrease, the probability of T controlling at least m seats weakly increases. So this is really the axiom that we feel captures the full range of possible non-monotonicities we might want to avoid in an apportionment setting. Selection monotonicity is important, and threshold monotonicity is a strictly stronger notion that captures a wider range of these non-monotonicities. This is what we feel is the right axiom that we should really be trying to satisfy. We can go one step further even and require monotonicity not just in the vote shares, but in the raw vote counts. And so that's an axiom we call vote count threshold monotonicity, which says the exact same thing, except instead of imagining the shares varying in a certain way, we imagine the raw vote counts varying in a certain way. And again, this is another strictly stronger notion. Vote count threshold monotonicity is the same as threshold monotonicity in the special case where the total population doesn't change. Then the vote shares are basically the same thing as the raw vote counts. So this is like requiring this threshold monotonicity even in the context where the total voter turnout changes. And so that's a stronger thing to ask for. So yeah, as I said, threshold monotonicity is what we really view as important. And unfortunately, despite a lot of effort, we're not able to show that Samford sampling satisfies it. This is the main open question left open by our work, and we think it's a very interesting direction for future work. The only positive result we do have about threshold monotonicity is that Grimmett's method actually does satisfy it, but only for coalitions T of size at most 2. And as we've seen, for coalitions of size 3, it doesn't even satisfy the weaker selection monotonicity axiom. Finally, for vote count threshold monotonicity, turns out that's actually too much to ask for. In our paper, we have an impossibility theorem that it is impossible to satisfy vote count threshold monotonicity along with the other non-negotiable axioms of ex post quota and ex ante proportionality. There are other results in our paper that I didn't cover in this short presentation. We also have an entirely parallel set of axioms considering pairwise notions of monotonicity, where you have a pair of different coalitions that you care about, and you just don't want one of them to go up and one of them to go down, both in non-monotone ways. And this is in the style of Belinsky and Young's population monotonicity axiom. This is a whole separate set of results. We have positive results and possibility theorems for those as well. We think the ones I presented in this slide in this presentation are the more natural ones, but we also have this entirely separate set of results as well. There's also a theorem in our paper that selection monotonicity implies Lipschitz continuity, and as I mentioned, we also show counterexamples for a couple other well-studied rounding rules, not even satisfying the most simple axiom of selection monotonicity. So all of the results I talked about in this presentation are summarized in this table, and the main big open question is whether Samford rounding or some other rule satisfies threshold monotonicity. We do not know a rule that provably satisfies it, but we view our main result that it satisfies selection monotonicity as a very encouraging first step because so many other rules fail that, even that axiom. Finally, another conceptual direction for future work is to figure out if there are other compelling axioms we could formalize that capture this notion of bizarre correlations between which states get rounded up. We took the perspective that bizarre correlations are correlations that are non-monotone in the joint inclusion probabilities. But there may be other things that can be formalized that would make sense as types of correlations to avoid, and it would be very interesting to study those in future work. Thank you for listening.